let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1203. We're in the middle of some problem set last time, which was yesterday. So let's jump back into it. So we were talking about optimization, making something as good as it can be within certain constraints. So we're going to continue with that. We had one last example to do before we embark on a different topic, chapter 5. So we're going to do section 5.1, which I hope to cover today. Most of it will be a conceptual discussion, and we'll have a few examples. At least that's the plan. So let's actually get through it. So last optimization problem we're going to do. The manager of a department store wants to build a 600 square foot rectangular enclosure in the store's parking lot to display some equipment. 3 sides of the enclosure is built of redwood fencing, costs $14 per running foot. The 4th side will be built from cement blocks that cost $28 per running foot. Find the dimensions of the enclosure that will minimize the cost of building materials. Okay, so this guy wants to build a rectangular enclosure. He needs to hold 600 square feet area, so that's right there. Area is constraint. It's the thing that's given, not the thing we can choose. And what do we want? Find the dimensions. That's the question we need to answer. And what do we want to do? We want to minimize cost. This is the objective. Okay, so now we know that. We go into our 6-step process because we know that this is optimization. And this is, my setup is kind of shifted here. Okay, let's do this. So course 1, and we read 2 diagram. Okay, so diagram here is of course a rectangle, but one of these sides is not like the others, right? So there's a side, one of the sides here is like a concrete. So that side is different from the other sides. So here, this is going to be, I'm going to call this length here X, because we need to find the dimensions. This length here, Y. And so that's our diagram, that's our situation. All right, now 3, remember what we do for 3, we set up constraint equations and the objective equation. Now the constraint is on the area. The area of this rectangular enclosure needs to be 600 square feet. So this tells you that X times Y must be 600. Now what is the objective? The objective is to minimize cost. Now cost is based on what the material is. So if I were to look at the diagram in terms of cost, so cost in blue, we know that the cement blocks, not concrete, cement blocks cost $28 per running foot. So because the cement is running for cement blocks running for a length of X, this is going to cost 28X for this side. Right? Otherwise, it costs $14 per running foot. So this side over here is going to cost 14Y. That side is going to cost 14Y. This side is going to cost 14X because that's the length per running foot. So ultimately, this means our cost is going to just be equal to 28 plus 14, 42x plus 28y. So that's our objective. That's our constraint. Can move on to problem part 4. In part 4, you want a new objective because your objective is in 2 variables, not very useful for us in Calc 1. So what we're going to do is we're going to solve for one variable in the constraint, plug it into the objective. Can solve for any one. Arbitrarily, I'm going to solve for the y because I'd rather multiply by a 28 than a 42. That's literally the only reason. Since xy equals 600, this means that y equals 600 over x. And so this tells us that our cost is going to be 42x plus 28y. So that's what goes in here because it's from 28y. Now, so that's our new objective function. And now step 5, we are going to maximize or minimize. Of course, we know the goal here is to minimize. So that's what we're going to do. Either way, though, we're going to find the derivative. We're going to find the critical points, all that good stuff. So we're just going to jump straight into C prime, which is going to be 42 plus, well, minus 28 times 600 over x squared. Set that equal to 0 or undefined. For critical points. Now, of course, undefined would occur when x equals 0. That means you don't have a rectangular enclosure. So of course you reject. So what you care about is this guy equaling 0, in which case you can bring that 20 times 600 over x squared to the other side. You can do your cross multiply however you want to do it. Multiply both sides by x squared, divide both sides by 42. The answer to life, the universe, and everything. And so x squared is going to be 28 times 600 over 42. Now, we can take 14 into 28 and 42, right? So 14 goes into 28 2 times. It goes into this 3 times. And then I can take 3 into 6, that's 200. So then I get x squared is 400. This means that our x is plus or minus the square root of 400. Of course, we're going to reject. Can't have a negative length. And so we ultimately have x is equal to 20. 20 times 20 gives you 400. But that's not where we stop. We still have to answer the question. Answering the question means we give the people what they want. They wanted us to find the dimensions. So we are going to find the dimensions, which means I need to know what the y is. So x equals 20. This implies that our y is equal to 600 over 20. 2 into 6 equals 30. So y equals 30. And so now I can answer the question. Dimensions are, it's a 20 by 30 foot enclosure where the cement runs along a 20-foot side. That will give you the area you want, and it will be the smallest cost. Yeah, so that's that. And another example of an optimization problem with the 6 steps. Read, draw a diagram that describes the situation, label it. Based on that diagram and labeling, figure out what your constraint equation and your objective equations are. The constraint is the equation that describes the restriction that you have, which is going to be the given value. So here you were given a value of 600. And then you're going to describe the objective equation, which is the function that describes the thing you want to make big, as large as possible or as small as possible. And you're going to get the new objective by solving for one variable in your constraint, plugging it into the objective. That puts it in one variable where now you can do calculus on it, calc 1 calculus. And so you find the derivative, set it equal to 0 undefined. The endpoint would be 0. So obviously that can't work. And so, you know, a local min is what's going to do it for you. There's one answer, you just assume that's the answer. And then finally, you actually answer what was asked of you in the very beginning. Okay. So that is that. And we ended just in turn. For our new topic. So we're going to go into chapter 5, where we are going to discuss integrals. So I mentioned from now on, because we're going into finals week, I want to make things as easy and efficient as possible. I'm going to start pre-typing the notes. You guys can get them ahead of time. So the next 2 sections are already typed. So what we're going to do on Friday is already typed up. It's in the, if you go into the notebook, it's in the other tab, which is this. So you guys can go read ahead, bring the notes with you to class so you don't have to really focus on writing notes. You can just focus on me explaining the concepts and going through the examples. But yeah, that's going to make things a little bit more efficient, I think. And I may even, I don't know if I can do this, but if I can, I'm probably going to do it. Our last class, which would be Wednesday, I'll probably do the lecture for that like asynchronously. So you guys won't really have to show up. And the last test probably would be asynchronous as well, to just give you guys a little bit more control over your time going into finals week. Yeah. Anyway, let's actually get to it. So we're going to talk about integrals. Okay. So throwback to way back when, pretty much the second lecture of class, I spoke about the 2 problems that calculus was meant to solve, the rate problem and the area problem. We've seen the solution to the rate problem, the derivative, and it turns out that that mathematical object is actually super useful for a whole bunch of other things. Not only can we find out how fast something's moving in relation to another, but we can find maximum and minimum values. We can do related rates. We can do optimization. We can figure a lot of things out. So it ended up being a very versatile solution. The other problem that calculus was meant to solve, as I mentioned, is something called the area problem. So the rate problem is kind of figuring out rates of change, how fast something is moving. The area problem is figuring out how much space something takes up. Now, we know a bunch of formulas from geometry for some nice shapes and stuff where we can know how much space they would take up. Like a rectangle, we know, oh, just take length times width. That's how much space it takes up. But what we're talking about is what if you had some weird random shape like this guy right here, right? What is the area of that shape, right? There's no geometric formula for it. And you might also worry about the question, well, why would I care about the area of some random shape? Because how much space something takes up is very important in general. One example could be how you're taxed based on how much land you own. The land that you own doesn't have to be a nice little neat rectangle. It can have all sorts of twists and turns on it. So when the taxman comes and says, oh, I'm charging you property taxes for how much land you own, you can ask him, well, how do you know how much land I own? Like, how do you know, right? So how do you know you're not being overcharged for taxes, or whether or not you should stay quiet if you're being undercharged? You know what I mean? Don't evade taxes. Okay, so yeah, that becomes a problem now. There are a lot of things that are based on how much space something takes up. So knowing how to do this is very important. And it turns out we've known how to do this for a very long time. There was this dude called Archimedes who back in near 300 BC was solving this problem, right? The problem you may have seen before is to just cut it up into familiar shapes that you already know the area of, right? So you have this weird shape. What you can do is you just dissect it into a bunch of rectangles. You know how to find the space that rectangles take up. And so what you can do is you can just count the number of rectangles and multiply it by the area of each rectangle. And of course, you might have these little crevices right here where you don't quite have a rectangle. You have just a little snippet of something. And you might just, you know, you might just, come on, iPad, pick the pencil. You might just estimate this. Can't put this guy. Okay, this thing seems to be on a different scale. Let me go down. So you might just estimate this, right? Say, it's about half a rectangle, about a quarter, right? You're not going to be exact, but that's the idea. You cut it up into smaller shapes and you define the area of the larger shape to just be the sum of the areas of the smaller shapes, right? Very basic solution. And it's actually a pretty decent solution, actually. You can get a better answer just by cutting it up in more shapes. So you can, if you really, really care about what that rectangle, one of these rectangles is worth, you can even go in and slice it up into even more rectangles and get a better idea. And eventually you'll get to some answer that you're happy with. I mentioned before that a lot of times in life, math helps you, it gets you an answer that is an approximation. It's not the real answer. And that's okay, because a lot of times having the real answer, we couldn't really use it anyway, right? So if I know the answer is pi, how am I going to get pi units of anything in the real world? No one even knows what all of pi is, right? So getting pi to a few decimal places is good enough for the real world, right? So yeah, you can get a pretty decent answer here. Now, the problem is this is kind of very work intensive. If I were to give you another blob of some other shape, you kind of have to go through this whole process of setting up rectangles again, and it would be like a whole new problem of counting. So while this does solve it, it's not very efficient and it takes too much manpower. So what we're going to do is kind of make this problem a little nicer, and we're going to use mathematics to do this. In particular, we're going to use functions and the xy plane to help us out. So thanks to Descartes, which we mentioned, who gave us the xy plane, what we can do is we can put the shape on the xy plane. And then we can start to talk about now, oh, we can think about the shape as a function of something. And so what do? So first thing is you have to make it a little bit simpler. So you take your shape and you know you want to dissect it. But now if you're thinking of a functions, dissecting it vertically and horizontally means you have to be paying attention to both the x and the y at the same time. That's kind of complicated. So what we can do is just decide to dissect it in one direction only and just take very thin strips that we know the area of and put them together. So you can have like these very thin strips of rectangles. Right? And you can judge it that way. You can still do the whole length times width formula. It's just now you have just very thin rectangles going in one direction. That would actually make things a little bit easier on us. We don't have to keep track of two variables at a time. By cutting it vertically, we now only have to track at what point on the x-axis we're at, so we can only track the x-axis, which is nice. So we throw this guy on our XY plane, and we're like, all right, we're in business now. We can start to look at what the area is going to be, but then problem, it doesn't pass the vertical line test. It's not a function. So then you're like, all right, what we're going to do is just take half of it. At first, just measure the area of the top half, and then we can measure the area of the bottom half separately. That way we pass the vertical line test, split it into two curves, take one curve at a time, and we're in business. We can now add up these rectangles and get to the area. So now you cut it up into these smaller shapes, which is going to be a bunch of rectangles, right? And you're going to notice that this guy you can think of as some sort of function, which I think I mentioned over here. So now what we have is a curve. We have a bunch of rectangles, and there's this curve here. So this is now a curve. Call it f of x, right? And now what happens is the area problem now becomes a problem of finding the area under a curve, right? It turns out, so it's in the same way, it's when we start to translate a problem from real life to mathematics, we want to have a nice, very numerical, very simple way to deal with a concept, right? So just like how when we started with the rate problem, how fast does anything move? That's so vague. We can't do anything with it. But what is the slope of this straight line? Very specific. We have a formula for it, right? So when we can translate that real world problem into a very nice mathematical idea, that's where the magic happens. So it turns out we went all the way from having to dissect things and count rectangles to let's figure out the area under this function, right? If we can do that, we can solve the area problem. If we can do that in a nice, sophisticated way, we can solve the area problem in a nice, sophisticated way. And of course, there is a nice, sophisticated way, or we wouldn't be here. An important idea is the more rectangles you use, the better the approximation. So if you look at here, I have two rectangles. It's a good approximation. It's decent, but this is better using 4. This is better using, it looks like 7 here, right? So we can get a better approximation by using more rectangles. Okay, that should be pretty obvious because what happens is we can get into these little nooks and crannies, these little crevices, and where we used to miss a big area, we can now miss smaller areas. So that's pretty straightforward, okay? But what if we're greedy? We don't just want an approximation. We want to know the exact area under the curve. How many rectangles would you need to fill in all the spaces? How thin would they have to get to fill in all the spaces? Well, I think you kind of know what the mathematical answer would be. You need an infinite number of rectangles, right? And they will be infinitely thin. They will have a width that we would call what is the word that we use for it? Infinitesimally thin, right? So that's like infinitely thin. When you say infinite, it kind of has the idea that you go big. When you want to go small to an infinite degree, you say infinitesimal. So we have an infinite number of rectangles, but they're all of infinitesimal widths. And I think I wrote that in the notes somewhere. I just drew a blank just now. Okay, so now we know a problem of how to approximate the area under a curve with a bunch of rectangles, and we have some notion of what it would mean to find the exact area under a rectangle. So this is going to lead us to the definition of a definite integral, right? So this is going to be the object we're going to use to measure this thing, right? So here is how we're going to actually do it. We have to come up with a systematic way of setting up these rectangles. You can't just, everyone just do the rectangles any way you want, right? It's not going to lend itself to a mathematical theory. So you want to be very specific about how you're setting up the rectangles. So what you're going to do is you're going to look at the interval where you want to find the area under it. right? And then you can call this first part x naught, call this xn, right? Imagine it on an interval a, b. So x naught would be the a, xn would be the b. And what we're going to do is we're going to choose where the endpoints of our rectangles are. So you would split this into what we call a bunch of subintervals, right? So you'd have like, let me not do that much because I'm going to be redoing this for the others. Where you have a predetermined length. Normally, we're going to want it to be of equal length, right? So this is going to be your x1, your x2, your x3, and then your xn is the x4, right? And make these the same width. Call this width. Delta x, for it's a change in the x values, right? Now, this brings us to the above, where if you have an interval and the length of that interval, of course, is going to be the right number minus the left number, b minus a, and you want to split it up into, say, n equal pieces, then what you would do is you would take the length of the interval and divide it into n pieces. So you would have the length of the interval divided by the number of pieces you want, which means that your delta x would end up being b minus a over n. It's a very important formula to remember. So for us, when we're doing this setup, delta x is going to be the width of each rectangle, and you can always find that width by this formula, b minus a over n, where n is the number of rectangles you want. So in this case here, we're going to have 4 rectangles, so it would be b minus a over 4, whatever the b and the a are. And now there are a lot of ways that you can actually construct these rectangles, but there are 3 important ways that we want to know. There's going to be a left-hand rule, a right-hand rule, and a midpoint rule, right? There's also a right-hand rule in physics, not that right-hand rule. We want a different rule to actually get these. Now, what the left-hand rule says is that we make the left side of the subinterval determine the height of the rectangle. So here is the first subinterval over here. I would pick the guy on the left, and that guy is going to determine the height, right? So the left side would go up, hit the curve, and then I cut off the height right there. Similarly, for the interval x1, x2, pick the left side, go up, hit the curve, cut off the height right there. And you continue this process. Right, and so, come on, iPad. And so the length of this, the area of these rectangles would be an approximation for the area under your curve on the interval AB, right? Now, of course, the height of these rectangles, maybe I should do that in a different color. The height of these rectangles will be given by the value of the output of the function. So here it will be f of x0 would be the height. Here it's going to be f of x1, here f of x2, here f of x3. Notice that if we pick the left, that the rightmost point, the f of xn, is not included because it's on the right side, but all the left sides are included. I'm going to evaluate the function at all the left endpoints. That's why it's called the left-hand rule, or the left-hand approximation sometimes. And you might notice in this case, if we want to actually find the area under the curve, in this case, for this function, it's what I'm saying here is not general. We get an underestimate for the area. Under f of x on AB. Because you'll notice that there's area in the top here that I'm missing. Right? So I'm going to have actually a little bit less than what the real area is if I only use the left. Right? Now, in a similar way, we can have the right side determine the height. So here is my x0, x1, x2, x3, xn, which is the 4, that's your A, that's your B. I can make the right side touch it, and that determines the height. Right side, touch the function, that determines the height. Right side, touch the function, that determines the height. Right side, touch the function, that determines the height. Now you're going to estimate the area under that function on the interval AB by the area of these rectangles. But notice that these rectangles actually have extra space that's above the function. So you're actually going to get a higher value than the actual area. So in this case, this gives an overestimate. Right? Because the function is increasing. So if you use the right side, you're always going to be a little bit bigger than the left side. And so you get an overestimate. So sometimes we don't want overestimates or underestimates, or we want to minimize the effects of having an overestimate or an underestimate. So what we can do is set up another rule where we use the midpoints. This is called the midpoint rule. And so what happens here, you'll notice that you can set up your x0, your x1, your x2, your x3, and your x4, which is your xn, which is your b. And instead of using the left or the right, what you can do is you can use the midpoint. So you define some new x values, right? Where this one is called x1 star. That's x2 star. That's x3 star. That's x4 star. And what you do is you let that point determine the height. So you let the middle of the interval determine the height. And now what you realize is that when you start drawing these rectangles, what's going to happen is the middle part determines the height. Here, the middle part determines the height. Here, the middle part determines the height. Here, the middle part determines the height. You'll notice that you kind of minimize the effects because on one side, you have an underestimate here, but then at the same time, you make up for it with an overestimate here. So with a midpoint and this kind of function, you kind of do an underestimate, but then you kind of correct it with an overestimate. So in theory, by doing it this way, you can get to the answer a lot quicker with less rectangles. You can get to a better answer, right? So that's another way of doing it. That's a midpoint, right? So in this case, this gives both overestimates and underestimates. So in theory, we can get close to the answer quicker. Or quicker is not a word, right? More quickly. Or I can be with fewer rectangles. Okay. So that in principle are the three ways that we can find the area. Well, there are more than three ways, but in our class, these are the three ways in principle that we want to find the area. Or more specifically, approximate the area under a curve, right? Now, these leads to some formula, for example. And let me just try to explain here. So each of these lead to a formula. Example for left, you would end up with the area is going to be roughly, you're going to have f of x0 times delta x plus f of x1 times delta x. You're just taking length times width, plus f of x2 times delta x plus alerts. Plus f of x3 times delta x. And notice that delta x is a common term, so you can even do delta x times f of x0 all the way up to f of x3 in practice. Another way to write this out is to just say I'm taking the summation of the f of xi times delta x, where I is going from 0 up to 3, right? Or more importantly, I is going from 0 up to n minus 1. Right? It stops just before the last endpoint. Right? So this is what's called the left-hand approximation. Using n rectangles, which in this case n is 4. So it's the abbreviation or the symbol that we use is big L little n, right? And by a similar vein, you can develop these other formulas, right? So you can have the left-hand approximation, which means you start at the leftmost point and end just before the last point. You can have the right-hand approximation where you're going to start at x1 and then go all the way up to xn because you're on the right side. And then for the midpoint, you're just going to be adding, well, the midpoint values. The outputs of the function of the midpoint values, all of those times the length. And that will give you the areas. So these formulas here are important. It's kind of known in principle. Right, so I already said this in words. F of xi is just the height of the rectangle. Delta x is just the width of the rectangle. So we're just adding up a bunch of rectangles. That's what these formulas mean. You're adding up a bunch of length times width. And your delta x is b minus a over n. And your xi star, these are just the averages of the two endpoints, because that will give you the guy right in the middle. But you can just find the average of the first two and then just add your delta x and it will give you the middle of the other ones, right? So the formulas above, these are called Riemann sums, named after a German mathematician, Bernhard Riemann. who developed this method of finding areas 100 years ago, roughly. He did a lot in calculus. So this method that we're using is not the method that Archimedes used in nearly 300 BC. The method that we're learning in Calc 1 class today comes from Riemann in, I want to say 1905, somewhere like there. Right, so they're called Riemann sums, right? And now, remember, when we want to find the exact area, we want to imagine that we can use an infinite number of rectangles. And what does that mean? Well, we now have the concept of a limit. So we just need to take n approaches infinity, right? And that leads you to this. The exact area is going to be the limit as n approaches infinity of this expression that we have for these guys. And in this point, it doesn't matter if we use left or right or midpoint, because they're all going to give me the same answer once I have an infinite number of rectangles. So the formula here is stated in terms of the right-hand rule, but it doesn't have to be the right-hand rule. It's just for definiteness. Stated with right-hand rule for definiteness. That might be a word, we don't know. And this is the notation we use for that. So whenever I take the infinite limit, the limit at infinity of a Riemann sum, I use this notation. Instead of using sigma, I use this little fancy, it's actually an S for sum. It's an elongated S. That S is called an integral sign. And what it means is I'm taking a Riemann sum, but I'm using an infinite number of rectangles, which is, right? So it's kind of like how we have delta x and dx and dy dx versus delta y and delta x. One is the crude way of just like counting stuff. One is the sophisticated way of using limits to find some. And that is what we call the definite integral of f of x on AB. So the definite integral is just a Riemann sum with an infinite number of rectangles. Now I'm gonna show you how to do that, find that guy by shortcuts soon. But today we're actually going to do the basic finite approximations. Just want to give you some notes on what we call stuff. The S is called the integral sign, the B is the upper limit, the A is the lower limit. The function in this case is called the integrand, and the dx is called the differential. This tells you that I'm slicing up the x-axis, right? So I'm just identifying who my independent variable is, who I'm slicing up the axis for, right? So this is the definite integral, and the point of it is finding the area under a curve. Okay. So now let's go to our finite examples. So this isn't the definite integral. This is just the finite examples. So, and I'll be asking you problems like this. So consider this function, y equals x squared plus 1 on the interval 1 to 5. I want to find, approximate the area under this function using 4 subintervals. I could also say, by the way, or 4 rectangles. Or I could say using n equals 4, which you would know means that by our notation means that we want to set up n rectangles. So I can say n equals 4. So we're going to do this the 3 ways: the left hand, the right hand, and the midpoint. I'm going to show you the process for each. And it's not going to be bad in principle, so it should be okay. So let's see how we would do this. So the first thing that you want to do is you need to find delta x, right? But we know that delta x is b minus a over n, right? So here we have the interval AB is equal to 1, 5, and our n is 4. So this means our delta x is going to be 5 minus 1 over 4, or it's going to be 1. So the rectangles are going to have length with 1, right? Now, what I like to do is like to draw the interval in subintervals. And put the numbers on it. So what I would do here is, here's the interval from 1 to 5. I know I am splitting it up into 4 equal pieces. And now I know the length of each piece. So what I do is start at the first one, and I'm going to add delta x to get to the second one. Then I'm going to add delta x to get to the third, to get to the first one, because we started at x0. So get to the first, you add delta x, and you just keep adding delta x until you get to the last number, right? So our delta x is 1 here, so I take 1 plus 1, right? That is 2. 2 plus 1, you get 3. 3 plus 1, you get 4. So those are all the numbers. Now you want to pick the necessary numbers. Here we're doing left hand. So the numbers on the left matter to me, which means I'm going to pick this, 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 that. So I'm going to pick the relevant numbers. These are the xi. So I'm actually going to use this to figure out the area. So now what I can do, the third thing, is to set up and evaluate the Riemann sum. Okay, so now I know my area. I'm approximating it with L4, which I now know is going to be delta x times f of 1 plus f of 2 plus f of 3 plus f of 4, right? So that's going to be, well, delta x was 1. F of 1 is from my function. Our function is x squared plus 1. So this is going to be 1 squared plus 1, 2 squared plus 1, 3 squared plus 1. And I'm adding these all together. 4 squared plus 1. Right, so that's my f of 1, my f of 2, my f of 3, my f of 4. And then you just compute what that is. So that's going to be 2 plus 5 plus 10 plus 17. That's going to be 34. My approximation for this area is 34 square units. So that's the left hand. Now, all the others are done very similarly. So I can go through these a little bit quicker. So it just matters whether you're choosing left, right, or middle. And that's the only difference, right? You're picking the different x values. So again, if I want to do right-hand endpoints, I would do 1, find delta x. Delta x equals b minus a over n equals 5 minus 1 over 4 equals 1. Set up interval. Okay, so I'm going to go here. I know I'm between 1 and 5. I want 4 rectangles. I know that this will be 2, 3, 4, and 5. And now I know I want the right sides because I'm using the right-hand rule. Third, I'm going to set up the Riemann sum. So now my area is approximately right-hand rule approximation with 4. In this case, that's going to be delta x times f of 2 plus f of 3 plus f of 4 plus f of 5. Right, so I choose different y values here. Now, that's 1. This is going to be 2 squared plus 1 plus 3 squared plus 1 plus 4 squared plus 1 plus 5 squared plus 1. Okay. That's my f of 1, f of 2, f of 3, f of 4. That's going to be 5 plus 10 plus 17 plus 26. The approximation here is 58, larger than the left hand. Okay, that's it. That's the whole answer. Normally, I won't ask you to do all of them. I just want to demonstrate all of them for you. I'll probably ask you to do 1, maybe 2. But the midpoints, same process. It's just which x values are chosen. So here I would find delta x. Delta x is always b minus a over n. That's 5 minus 1 over 4. I would set up the interval. So again, I know it's 1 to 5. Going to have 4 equal pieces. It's 2, 3, 4. However, I want the midpoints. What I can do is I can average these. If I take 1 plus 2 over 2, I get 3 over 2, which is 1.5, and that's going to be the middle here, 1.5. Now, once I have that 1.5, I can just keep adding delta x. To find the other middles. Of course, it's obvious here that this is going to be 2.5, that's going to be 3.5. This is going to be 4.5. And those are the x values that I picked. Now, finally, you set up the Riemann sum. Right, so this approximation is called M4 because I use the midpoint rule with 4 rectangles, and we're going to have delta x times f of 1.5, f of 2.5, f of 3.5, f of 4.5. Is 1.5 squared plus 1 plus 2.5 squared plus 1 plus 3.5 squared plus 1 plus 4.5 squared plus 1. That actually ends up being 45. Right? And that's it. These are all approximation. It doesn't guarantee that any of these are the real answers. In fact, we kind of know they're not. But if you kind of want to see, I'll just post it here. If you kind of want to see what these numbers mean and how they relate to each other, you can see this picture here, right? So the left hand is like the green rectangles. Notice that they gave you an underestimate. That was the answer 30 something, I think, 34. The right hand gave you 58. That's because the right hand, you had the rectangles above the curve. The midpoint kind of gives you both kind of in between. That gave you 45. For this kind of function, we kind of expect it to be closer to the 45. Next time, we'll actually see exactly what the answer is, or how to know exactly what the answer is. But for now, we will stop there. Yeah, that's it. So thank you for your time and attention. The notes for what I will be doing on Friday are already posted, so you can actually go check those out ahead of time. And yeah, that's it for now. Nothing else to really talk about. We start section 5.2 next class, and I will see you guys in the next one. Ciao.